Eh, bueno, pues buenos días a todos, a todas. Si me lo permiten, voy a dar el inicio en inglés para tener una atención con nuestro invitado del día de hoy. Welcome, Professor. We are thrilled to have you at our university. I will say the introduction, and then I'll hand it over to you. You will have 40 minutes for your webinar, followed by 20 minutes for Q&A. The University of Chihuahua, through the Faculty of Engineering, is honored to continue this cycle of conferences of the National Network of Water Postgraduate Programs. This is an initiative by the university to invite national and international researchers who study water-related issues to engage with our postgraduate students. Today, we continue this cycle of conferences with the presentation by Dr. David Rudolph. Dave needs no introduction. He has a PhD Earth Science in Hydrogeology by the University of Waterloo in Ontario. He carries out research in groundwater management with a focus on innovative ways to monitor water resources in the face of changed land use and climate. Professor Rudolph has different research interests, such as groundwater resource management, groundwater flow, hydrology, contamination, and remediation. And we are very happy to have you here. The floor is yours, Professor. Welcome to our university.
Bueno, muchas gracias y lo siento mucho que no puedo presentar la charla en español por español hoy, pero tal vez en el futuro voy a tratar en otra vez. Pero después varios años sin práctica, ahora estoy muy fuera de práctica. Entonces, gracias a Dios, puedo presentarlo en inglés. Gracias. Okay, well, welcome everyone. It's such a wonderful opportunity to be with you. Professor Gonzalez, thank you so much for the invitation. I've been looking forward to this. And today what I'd like to do is talk to you a little bit about the impact of climate warming as we're all dealing with it as engineers and hydrologists. And I want to talk about a place that maybe you wouldn't frequently hear about, certainly not study as much in northern Mexico, and that's in the northern landscapes of North America. So almost at the edge of the Arctic Circle. So even in this very remote landscape, hydrology and hydrogeology, as we often work on the problem, is very much a significant concern and issue and changing very rapidly. So the place I'll take you today is probably warming at a rate 3 times faster than most parts of the planet. And as a result of that, this cold environment that you see in a picture there is warming rapidly. So the impact on the hydrology is extreme. And I want to share some of that with you today. So if you look at how groundwater is used in the north, it's not terribly different than what you might think of in almost all applications of groundwater as a resource. It's used as a drinking water source, of course, all throughout Mexico for sure, but also wildlife uses it, depends on it. In the north, there's much more wildlife than there are humans, as I'll show you. It's not very populated area, but it's extremely critical for us because of the resource industries that are there. So petroleum development, mines, forestry, a lot of our resources, and Canada is a resource-based country, is derived from the north. So lots of water is required for developing the resources. All of us as geoscientists understand that being important. From an ecological point of view, of course, groundwater sustains most surface water systems, as we all know, through base flow, wetlands and streams, also provides nutrients to keep ecosystems balanced. In the north, one of the other issues that's critical is that groundwater plays a major role in controlling where wildfires occur. And I'm sure you've watched the news over the last several years and seen so much of Canada burning, and this year badly again along the west coast and in the north. I've just returned from the Northwest Territories where we'll visit today, and the sky is becoming full of smoke again as a result of the fires. So groundwater plays a big role in that. One area that we do a lot of work on, which I'll do a little bit of discussion today, is how groundwater in this complex system can deliver contaminants to the surface. This is one of the reasons we got involved in it. But a very unique aspect of the North is this occurrence of permafrost. So again, certainly nothing you're going to find in and around Chihuahua, but in Canada, a lot of the Canadian landmass is underlain by permafrost. So let's focus a bit on that. From a hydrogeology point of view, you can think of permafrost as being an aquitard, really, where the subsurface is frozen. So it's essentially impermeable to the flow of water. But as the permafrost degrades and thaws, all of a sudden these aquitards start to disappear. And that completely changes the flow system, surface, groundwater interactions, etc. And we'll explore that a little bit here as we move along. So moving up into the northern part of North America here in Canada, this map gives you an indication of where this permafrost is. And we define permafrost as being soil or subsurface materials like rock that remains below freezing or lower for at least 2 consecutive years. So in most cases, it's much longer than that. But as you see in the diagram above, if you can see that, where the pink is continuous, the permafrost can be almost 1 kilometer thick. So we're talking extremely thick, frozen ground. As we move a little bit towards the south, there's a trajectory as we get warmer and warmer moving to the south, where the permafrost becomes discontinuous or sporadic, and finally it's completely gone in the southern part of Canada. So that's an indication of its distribution, sort of currently. And this diagram we've got here is one that all of us as hydrologists are quite familiar with, showing sort of the way the water balance is set up throughout the world. And we're mostly interested here in freshwater. But what I wanted to point out, and of course, this is always a challenge for us to explain, that groundwater really is a much larger reservoir than surface water. Professor Gonzalez just returned from Canada seeing the Niagara Falls and thinking about how much water is linking between the Great Lakes there. It's such an enormous volume of water that it's hard for people to believe that groundwater is much bigger than that reservoir. So we have a hard time explaining it, but it's really critical. So if you look at the top there, a small 1% of fresh water being open surface water and other types of water. Well, interestingly, this ground ice or permafrost that I'm talking about is probably 3 times as large as a reservoir than all of the lake systems combined. So the thawing of the permafrost in the subsurface will release in the near surface a remarkable amount of water. So that just gives you an idea of the water balance and how important this permafrost may be as it starts to thaw. So let's take a little trip 5,500 kilómetros más para el norte, way north, to a small town where we've worked for the last 6 or 7 years, a town called Norman Wells in a part of Canada that actually is a territory. Most of Canada is a series of provinces, sort of like the states in Mexico. But in the north, we have somewhat younger provinces that haven't established completely as provinces, and they're called territories. And one of them is the Northwest Territories. So the diagram there to your right shows the nature of permafrost in this area of the world. And where we're going to go, Norman Wells there, where that gold star is in a discontinuous permafrost environment. And again, as I mentioned, this area is warming on average about 3 times faster than most other monitored locations, certainly throughout North America. And Norman Wells is a really interesting story. So when you're absolutely bored, nothing to do, and you're interested in earth sciences and geosciences, look up the history of the Norman Wells oil fields. So people coming down the Mackenzie River that you can see in the top left picture found oil spills and oil slicks pouring out onto the river. And they realized that there was a resource of oil here, and they went up to this very, very remote world and started to develop that oil in the early 1900s. That was turned out to be Esso, or Imperial Oil's, first major oil strike. So that it's the fourth largest in all of Canada, enormous. In fact, they've extracted this oil through a big, as you can imagine, network of wells, but some of them are built right in the middle of the river, and that's that bottom corner where they built artificial islands and drilled to pump this oil out. And they've been pumping it still till today. It's still in operation, but it's slowly getting to the point of being closed for over 100 years. So a massive development there. When they started working up there, this was how they advertised for workers, and this is what I tell my grad students when I try to convince them to come up north and work with me at this site. So this is an ad saying that the working and living conditions in this area are so difficult as they could be encountered anywhere in the United States or in foreign territory. People hired for this job would require to live under extreme conditions, temperatures ranging from plus 90 or 90 degrees above zero to 70 degrees below zero, fighting swamps and rivers and ice and mosquitoes and flies, not only harmful, but would do bodily harm. So if you're not prepared to work under these conditions, don't apply. So my grad students read this and think, well, do I really want to go up north? Turns out there was enough of them that would have come up north. So I've got some information to share with you today, but quite a remote world. So let me take you up to a field site. In the top left corner is this town of Norman Wells I showed you the pictures of a moment ago. And just on the other side of that river, by the way, the Mackenzie River is Canada's largest river. And if you see the scale at the bottom near Norman Wells, the river is over 3 kilometers across. So this is a very large river. On the other side of the river is a small watershed where oil companies were exploring for shale gas and shale oil very recently, within the last 10 years. And they asked us to help them understand how groundwater is circulating between the lakes and the deeper systems there as they decide whether they can do hydrofracking, can they extract oil and gas from this part of the world. And that is how we started working on this. And then realized it was also an incredibly interesting site to work on, to observe change in climate and how those changes are influencing the hydrology of a northern watershed. So we'll focus on that area for our talk today. So let me show you sort of a diagram of how we conceptualize the subsurface here. So there's that big river in the middle, and in the subsurface are areas of frozen soil, permafrost, that it's discontinuous. So places where it's not is not frozen, the surface water and the groundwater are interconnected the way you would normally anticipate it in most systems. Where the ice is still frozen, groundwater can't flow through it and has to flow around it. So you can imagine as the permafrost degrades, it changes the flow system in the subsurface. And I'll show you what types of changes that occur in that. The small plot of temperatures on the right-hand side shows you the increase in average annual air temperature since 1940 at the town of Norman Wells. And you can see close to a 4 or 5 degree change over that time period, a 60-year time period, which is really high. So it's warming very rapidly in this area, and we're anticipating it's changing the subsurface as well. So if we sort of zero in on a small part of the subsurface, just to give you a conceptualization of what it looks like. So where the permafrost is continuous, the lakes and the streams and surface water systems flow on top of the frozen ground. So that area there is really referred to as an active layer, where things freeze and thaw during the course of the year, and then the streams and lakes circulate during the warm times of the year. So as the climate begins to warm, you can see that the permafrost starts to degrade. Some places open. The term talc is used as an area that's thawed within permafrost. An open talc means that water can pass through it. So the lower diagram is showing you how the flow system is starting to enhance. So lots of changes. I've just summarized a few points at the bottom there. In the groundwater surface water interactions. So changes in flow rate, changes in base flow, circulation of deep groundwater with shallow groundwater, all of which is happening quite quickly. And the concern is, or to learn more about that, as it will affect the ecology, it'll affect how people develop the resources in the area. And of course, as you will know, as permafrost thaws or ice thaws, it changes its volume. So it generates local land subsidence, which changes, of course, the ground surface and lakes and drainage systems. It also influences how large animals will migrate. So the First Nations people that I work with in this area are very concerned, obviously, about wildfire, but also very concerned about where the animals migrate because they hunt them. And they need to know where they're moving. So the thawing of permafrost, as a hydrogeologist, we now have a role to help in maintaining the livelihood of the First Nations there. And I mentioned something about the release of contaminants. One thing that you may have heard of is the release of carbon. So in the north, with the concept of the permafrost thawing, the concept is that it may release an enormous amount of greenhouse gas that has been entombed or trapped in the ice for 10,000 years and now will be rapidly released. So this is something you may have heard of or read about. We'll talk a little bit about that. So the challenge is then, if we're asked to do more sort of classic groundwater investigative work that you may all be familiar with, the problem in this type of environment is that so you can probably imagine, access to this field sites is essentially almost impossible, but certainly very limited. So that restricts what you can do in the field for your data collection. It's very difficult to get into these locations and to do some work. And of course, using conventional systems like we're used to, drilling, installing monitoring wells, taking samples and collecting subsurface samples is really, really difficult. So mapping groundwater flow phenomena that you might normally do if you can travel across the countryside and do it is very difficult. And actually, the question we are asked frequently is, where's the permafrost and where is it discontinuous? All difficult things to measure. So challenging then for us as hydrogeologists and geoscientists is, well, what do we do then in this area? What do we have for options? So what we've been working on, the little picture there in the right shows you what the terrain looks like. So you can imagine the only way to access this is by helicopter. So what can we do to start characterizing and collecting some information? Well, the first major set of tools are remote sensing tools. So satellite-based imagery, low elevation remote sensing with either airplanes or helicopters that can characterize the subsurface, and then we can interpret it to help learn about how groundwater and surface water is interacting. And I'll tell you a little bit about that as we go forward. Then based on this remote sensing, can we target specific areas of interest that we can go to with our very expensive helicopter and do a very focused site characterization, carrying with us portable tools, simple light systems that allow us to interpret the hydrogeology and the geochemistry of this water system. And of course, applying geophysics, as you can imagine, would be a great option. So let me start just by showing you some of the tools that might be of use from a remote sensing point of view. So I'm going to talk about three scales and targets of remote sensing that one could use here. The first one is a satellite-based optical imagery system. Fortunately, the ground surface throughout the world is photographed regularly, and it's available. You can buy it, you can get it free in many cases, and that can be used to help do some reconnaissance level assessment of the ground surface. I'll show you why that's useful. The second one is using infrared imagery. and probably you've run across this before, but this is a way of detecting temperature change, so water temperature change. And why would that be important? Because where we have a good contrast between groundwater temperature and surface water temperature, we can detect where groundwater is discharging based on an infrared camera. So we'll do that from a helicopter, and I'll show you the results of that. And then finally, one that we've just recently applied is an airborne electromagnetic system that uses a very new type of technology that measures the electromagnetic signals at different depths and provides us with a way of mapping where the permafrost is located, because obviously frozen soil is highly resistive compared to thawed soil. Okay, so think about that in terms of how geophysics could be used. So the first thing I'll show you here is how the remote sensing from a satellite-based system might help us. So in the northern environment, of course, we have a very long, cold winter. So any groundwater that's discharging to the surface, if it's discharging continuously through the winter, it will freeze once it gets to the ground. So think about a groundwater spring that you may have encountered. Throughout this northern landscape, there are groundwater springs. They're just very hard to find. One way to find them is to see them forming during the wintertime. So when it's cold, the relatively warm, and I say relatively warm because the groundwater really doesn't get much warmer than about 3 or 4 degrees Celsius in this environment, comes to surface and flows on the surface, and it's like there's an artesian flowing well that comes to surface, and in the spring it starts to generate, or in the early winter it starts to generate a small pad of ice. Over the winter it gets larger and larger. Now, why would that be of use? So in the summer, when it's warm, you don't see the occurrence of this ice. But in the winter, these large areas of ice start to form. So the picture in the middle shows you in the middle of winter with these pads of ice forming. In the springtime then, when the snowpack melts back, it leaves the location of where these big ice features are. And that directs us right to points of groundwater discharge. So if you can find them, that helps us to direct where we're going to go with our helicopter, where we can sample from an airborne satellite-based system. So the question I asked my grad student, Brittany Glass, who did her work a few years ago, was where do these icings occur within our interest, our watershed of interest? You can see there that small watershed inset. How large are they, and do they occur at the same place every year? So she needed to go and take images in the summertime, take images in the spring, take and remove all the water features and isolate where these large ice features were. And fortunately, there were algorithm processing packages that could help do this. So she went through step-by-step mapping out where the water was, erasing those water features from the signal, from the optical signal, located where the icings were, and then compared them over a period of 20 years and found where they continuously showed up. And these points then are places that we visited, understanding that they would be areas of groundwater discharge. That provided us with a way of getting samples of water that was coming up through the system deep in the subsurface, but also places where there was an open and connected system between the deep and shallow systems, and the permafrost had degraded. So it helped us find areas where the permafrost was degraded just from a satellite image. So in order to get a little bit more, let's say, a local type of a survey conducted, we then connected with a colleague of mine here, it's Brewster Conant, who's doing the survey for us. And we're using a helicopter we're only 300 meters above the surface, and flying over it with an infrared camera, with a video camera and a GPS so we could map this. And now what we're looking for in the middle of the warm summer is cold groundwater discharging to the ground surface that you can see clearly with a contrast in temperature. So let me give you an example. So the picture on the top would be what it would look like from the helicopter looking down, and there's nothing there that would tell you that there's a groundwater seep. It'd be very difficult to make that conclusion. There's some surface water there, but it's not necessarily a seep. when you take a picture of it with the infrared camera, you can see how different the temperature is. And that was one of the areas that we found as a groundwater seep. So you can fly this over the area you're interested in. You can even use a drone for that. And you can map out the locations of groundwater discharge using the infrared camera. And let me just see if I can get this to work for us. This is just an image from one of the, as we were flying along. Sorry if this is too loud. Maybe we can turn it off. Try to keep them. So this is what the ground looks like. That's an old road, drilling road. And we're looking now at the subsurface here. And you can imagine it's very difficult to land and work in an environment like that. But the infrared signal on the bottom shows you where the stream is, and then immediately helps us to detect where there's very cold water. So there's a groundwater spring, and there's another small one there. So you can imagine we had kilometers of that type of infrared information. We use that to pick groundwater discharge points. Now, the last thing I'll show you here, just keeping an eye on the time here, is our geophysical mapping with this new system of airborne electromagnetics. So this system, called the Resolve system, it's commercially available. It's designed to not only use a single frequency coil of electric field, but a total of 6. Each one of them is profiling at a different depth in the subsurface. So we can profile up to a depth of 100 meters, flying over the ground surface, maybe a height of about 100 meters or so, maybe a little even lower, probably closer to 50. And flying back and forth over the ground, you can image the subsurface with the idea of mapping where the permafrost is. So this was our hypothesis, that the electromagnetic signal measured at different frequencies would allow us to simulate and measure the near surface, and then deeper and deeper as we go, so that we would have a profile. So this is the areas that we actually had a chance to do our flying and our surveys on. The two sort of gray areas there are the flight areas, where the surveys were conducted. The one in the top left shows you covering many different types of lakes, different sizes of lakes, and where we saw the groundwater discharging with the remote sensing data. And the other patch there goes right up to the Mackenzie River and across it, so that we can determine whether these lakes influence the continuity of the permafrost. And just as a couple of examples for you, this is a whole study of its own that one of the PhD students is working on now, but you can see the red is the resistive. So the top one, that's only down maybe 10 meters or so. You can see where the permafrost is consistent and continuous as you fly across it. So we have it at 2 meters, at 8 meters, 10 meters, all the way down to 100 meters. There's another one down at 26 meters where you can see that most of the permafrost is gone, and there's a very high conductive section right through the middle, which turns out to be a large discharge area in the bedrock. And this is following a structural feature, a big syncline, and the axis of syncline and some faults. So very useful for us to use this type of information to kind of track the occurrence of the permafrost. So the last thing I'll show you from the geophysics, here's a couple of lines that were going specifically over surface water bodies. The one in the top shows you that as you get to the edge of the lake, the permafrost is completely gone. So underneath the surface water bodies, we're able to see that the permafrost has thawed. It's still solid on both sides of it, but right where the lakes are, it's already has decayed and is gone. So this helps us with a conceptual model if we're going to simulate this watershed and do a water balance, as you imagine we would probably try to do as we move forward. And the one on the bottom shows you again how irregular the permafrost is next to where the surface water bodies are. So very, very useful tool, again, as a remote sensing tool to map the permafrost. So once we had that information in our hands where we thought there was groundwater discharging and interesting locations to visit, we were able to get a helicopter and a very talented pilot to take us to these sites and land and let us out to do some sampling. Of course, we took surface water samples, used very simple systems. So the picture in the middle are small drive point monitoring wells that are hammered in by hand. There's a small device just in the absolute center. It looks like a little silver cross thing there. That's just a probe that's pushed down into the groundwater that you can take a sample from. So we carried these devices with us throughout the area and sampled shallow groundwater. We even took a small system to take a core. So this is a gas-powered auger that we could use as a small group to take a core of the permafrost and take it back to the lab for analysis, all of which is portable, easily moved with the helicopter. So installing these manual wells allowed us to take water samples and also to measure hydraulic head. So for an example, there's this small probe pushed down into the edge of a surface water body, and you can see that the groundwater is discharging there as the hydraulic head is well above the surface water. So taking a sample there, I know I'm measuring and capturing groundwater that's discharging into the bottom of this small wetland. And we use that throughout the area to collect groundwater samples. So then the question is, what can we do with those groundwater samples? So depending on what your concern is, you can analyze the water for any type of geochemical or isotopic species. So I'll show you just a few of the data sets here. So we can talk about that a little bit. Obviously, major ions gives us an idea of what the geochemistry looks like, and maybe the deep and the shallow waters and the surface waters and groundwaters have very distinct signatures. So we can use the geochemistry to determine whether we're sampling groundwater or whether we're sampling very recent precipitation melt. In this area, as I mentioned, was an area that was targeted for shale gas fracking. So there's a major concern as to whether these organic compounds occur at the surface before they start fracturing. This is natural discharge of petroleum at the surface. We certainly know it was discharging into the river up near Norman Wells. So here we found it discharging into the shallow subsurface as well. And then we used some isotopes that you'd be familiar with, oxygen, deuterium, some tritium work. We did some strontium and methane, a variety of different things, looking at isotopes to try to track the occurrence of water. And again, super talented helicopter pilot agreeing to land right on the edge of a lake. You've got to be very lucky to have that type of pilot. So back to our little watershed here, there's a series of sampling points at lots of different types of settings, in the streams, in the lakes, groundwater, in the springs that we identified with the remote sensing. All of those samples were collected and then analyzed for that list of species that I told you there. You might be able to think of many others that you would add to it. But from this point of view, let me share just some of the results. So clearly, if you plot the basic ion chemistry in a very simple Piper plot, you can already see how the different waters cluster in different areas of the geochemistry. So the deep groundwater is so different than the shallow groundwater, and surface water also having a very unique signature. So this is helping us now to understand the conceptual model of the subsurface, where the groundwater is discharging. Is it coming from deep? Is it coming from shallow? So the simple tools like this are helping us. You can also do that with isotopes. So here's just a simple plot of deuterium and oxygen 18. And again, the lakes, as you would expect, are evaporated, so they're enriched. The water that sits right near the ground surface is very close to being precipitation values. The icings that were measured in the wintertime showed signatures close to the deep groundwater, and the deep groundwater, again, shows very old, very light, probably recharged back in Pleistocene time. So this water is quite old, and you can pick it up with the isotopic signature. So just sort of close to the last thing I want to share with you then, if my role here was to try to find places where groundwater was discharging, let's say where groundwater was manifesting itself at the ground surface, and I presented these results that I've shown you here today, most of them anyway, to my colleagues in the North, who are my First Nations collaborators. And these folks have lived in this area forever and are very familiar with it. And after presenting this, one of the elders said they were happy that we came and presented the results, but they said, boy, this sounds like this must be very expensive to do all this work. He said, if you want to find where the groundwater is discharging, where the seeps are, where the springs are. Just follow where the animals go. They will go to where the springs have salt in them because they desperately need salt. This is a very freshwater environment, and these large animals, this is a caribou herd here, moving towards a spring. Sure enough, if you look at the air photos, you can find the animal paths, and they go right to where the remote sensing systems found these springs. So we probably could have found most of these just by looking at paths that animals are moving in. So an example, here's caribou just digging down into the ground to get that salt out. And sometimes you have to get really aggressive to get that salt out. But this was a way that the First Nations shared their traditional knowledge with us. And we use the animal walking paths and hiking paths all the time now to learn more about the countryside. So it was very, very useful for us. So just to summarize this, the combined remote sensing tools that we used, and I'm sure there's others that you could think of, help to interpret how the groundwater system was actually functioning. It was invaluable insight that we wouldn't have been able to get because we can't get a drill rig into that area. It's difficult to do the type of work that we all would be used to from a hydrogeology point of view. So remote sensing is very valuable, and let me say it's probably valuable for you as well in different settings where groundwater is discharging in springs. We're certainly seeing that this thaw and permafrost is changing the circulation in the subsurface and the interaction with the land surface, and it's happening rapidly. So from our point of view, this is a rapidly changing groundwater system. There's very few environments in the world where you would see the actual geometry of the subsurface from a hydrogeology point of view when we think of aquifers and aquatards actually changing rapidly in time. This is changing, and it's hard to keep up with. So as we take this data and put it together, we're providing this information to our numerical modelers who are now trying to predict, as this warming continues, what will happen in the landscape. What will the water balance be like? Where will the ground subside? Where will it change its direction? And you can imagine if you're trying to put a pipeline through the ground that's subsiding differentially, it's very difficult for any type of buried infrastructure as the permafrost thaws because it can easily crack and bend and twist. And I'll just say that if you're fortunate enough to have traditional knowledge shared with you, wherever you are, take advantage of it. Listen carefully. It's just a gift because they're there all the time and they know so much about it. Nature tells them how it's working and they share it with you. You're so lucky. So just let me summarize here with the support of our research team. This is that old drill road that we land the helicopter on occasionally. Going through the study site. So the government of Northwest Territories has supported us. The First Nations Renewable Resources Boards, the folks that live in this area have been our partners. Fortunately, one of the oil companies is also supporting us. And we work with a couple of different universities, mine and also Wilfrid Laurier University here in Waterloo, and a series of faculty members and students who have been up working on this site since for the last close to 10 years now to collect these types of information. So finally, let me say that send a message to all of you that come up and visit Canada. You can see one of your local Chihuahua paisanos here. And if you ever get a chance to come and visit, put the northern part of Canada on your bucket list and come and see it. It's just amazing. And with that, Miguel, I'll come to an end here. I think we're just about on time.
Yeah, we still have time. Well, thank you for that presentation. It has been really interesting. We have some comments here in the chat. Saludos de Uruguay. Aquí son las 13 horas. Dear Miguel and Dave, thank you for this amazing initiative and nice presentation. Let me know if you're planning to share the presentation and any other material you consider. Nice dog also. So I don't know, Professor. Is correct if I is that correct? If I can I share the presentation?
Yeah, no problem. And I think you've recorded it.
Yeah,
Do you need me to send it to you as a PDF?
yeah, that would be great.
So I'll just turn it into a PDF. It's much easier to send than PowerPoint slides.
Cool.
If anyone would like it, that they're happy to. And then if anybody has questions, they want to contact me directly, I'm very happy to.
Well, we have some questions that students have sent through the chat. Uh,
Excelente.
how do you imagine groundwater modeling will be like in 50 years?
Yeah, so very good question. So one of the reasons we're doing this work now is so that we can track it in time to see how it changes. So the groundwater modeling tools that people are using include the process of thawing soil, and that's a very complex process. So the models have to respond to the energy coming into the subsurface that causes the ice to thaw. It opens the subsurface up, and groundwater starts cycling more rapidly. And things that are important about that, the modeling that people will do 50 years to propose 50 years, we're actually simulating this 200 years into the future to show complete degradation of the permafrost. And the ground surface changes its shape. All of the chemicals that are entrapped in the permafrost that are discharging come to surface and are discharged into the surface water bodies. The models can capture that now. What we really missed was actual field data so we could inform the models. Up until now, the models have been very speculative. We've just used them to say, this is probably what's going to occur. The data that I've showed you today now is helping us to inform the models moving forward. And that's another area of research that we're working on. So 3 of my students are just numerical modelers, and they're trying to simulate these complex freeze-thaw scenarios and changes it's a geomechanical problem because it subsides. And by the way, that was my work working when I worked in Mexico City, was looking at the subsidence of Mexico City. That was actually my PhD research. So I'd full circle back to looking at subsidence as far away from Mexico City as you can imagine up here in the north, but similar geomechanical problems. So great question.
We have another question. It says, do you believe that there will be a massive migration in Canada in the 21st century due to the forest fires?
So a migration away from the forest fires, you mean?
Yeah,
I guess
I
that's
think
it.
so.
Yeah. So what's interesting about the wildfires is that once they burn, it usually takes many, many decades before they can grow to a point where they'll burn again. So most importantly, we're trying to learn where the wildfires will probably occur to be sure that people aren't near them, try to control them as best we can. But you maybe heard the news, one of our big tourist spots up in the Rocky Mountains, a town called Jasper, it burnt severely just a month ago. So in terms of migrating away from it, I think the population is continuing to grow. People like to be further to the north. So I would say that controlling the wildfires, including how groundwater influences wildfires, it's really interesting because when the water tables drop, the soil gets drier and there's more fuel to burn. When the water tables come up, which they do in some cases because of the thaw of the permafrost, there's less threat to wildfire. Only the top trees burn. It's not the deep burning that's occurring now. So I think probably we'll learn more about how to control wildfires, but I suspect it won't chase the people away. People will still want to be there.
What is being done well in Canada related to climate change? What can be improved?
Yeah, so let's start with the second one. What can be improved? There's such a global effort to start reducing the use and dependence on fossil fuels. And Canada is a large supplier of fossil fuels. Well, so is Mexico. Both of us are,
Yeah.
are large providers of fossil fuels around the world. So part of the concern is, because it's so economically important for both our countries, if we stop production of this, we need to have another economic direction to go in. So what the Canada's trying to do is to move more towards a hydrogen-based economy, where the resource of developing hydrogen for energy is slowly going to take over from using fossil fuels for burning. Fossil fuels are still so critical for other things, for medicines, for lots of different things. But for burning fuel, we have to do better at finding ways to reduce our dependence of our economy on fossil fuels. That's a huge problem for us in Canada. What we're doing well, I think there's an awareness that we need to reduce that. People are looking towards electric cars, but of course that's not I don't think that's going to be the easiest solution. We're doing much more green renewable energy sources, solar, which of course would be quite useful in northern Mexico, maybe a little less useful here, but still we're using that. Lots of wind turbines, and moving towards hydrogen. So we have a new relationship with Europe on developing hydrogen generating plants for energy generation. And I think that probably those of you that are just studying now and moving into your careers, you will have hydrogen as being one of the things to be concerned about or working with. A very good opportunity. My son's a chemical engineer. He's studying chemical engineering, and he's very interested in hydrogen and how it can be used as a cleaner energy source. So I think Canada's not very, we're still far behind in terms of where we should be from a climate change point of view.
The last question is, are there other examples of successful groundwater modeling around the world?
Yeah, so groundwater models, well, we should interpret that question, meaning a global model, or examples of models that are, because groundwater modeling, of course, is used all around the
I
world in so many applications.
I think it's the first one.
So a global scale.
Yeah.
Yeah. So what a really good question, because the folks that we're dealing with now that are developing these models, and maybe I'll be able to send you Miguel, I'll send you some connections to this, are doing Canada-wide models. They're doing North American scale models in order to look at the influence of climate warming. And of course, as we all know, these climate models are so difficult to put together. They all seem to give you different numbers and different answers. So people are using a wide range of climate driving models and simulating integrated hydrologic systems. So groundwater, surface water interactions at a very large scale. That is an area of active research right now. So really great question, because it's right at the forefront of what groundwater modeling is doing. And I can provide you with 3 or 4 recent publications for whoever's interested in that, with the hydrogeosphere model and a few other big models that people are using for that. So I'll please remind me, and I'll get those papers. That was a great question.
Yeah, for sure. ¿Alguien más? ¿Otra pregunta? Si alguien quisiera hacer un comentario o escribir en el chat, yo lo puedo comentar aquí con el doctor Rudolph. ¿Alguna otra pregunta? Eh, ¿Algún otro comentario?
¿O interesa visitar el norte de Canadá?
Alguien que quiera ir al norte de Canadá? Eh, well, with this, we will finish. Again, I want to thank Dave for being here. It has been really, really interesting. I will send you the acknowledgement by email in the next few days. And some few words, Dave, before we finish.
Sí, la próxima vez vamos a reunir en vivo en Chihuahua. Me gustaría mucho visitar esta parte de México. Yo conozco varias partes de México, pero el norte, solamente Ensenada, esta área, en la baja, pero no en el centro, no mucho. Entonces necesito una invitación a visitar el famoso Universidad de Chihuahua.
Bueno, eres bienvenido. You are welcome to be here at our university. Thanks again.
Pleasure.
And with this we will finish. So thank you for being here. Gracias a los estudiantes, gracias a los maestros.
Gracias a todos.
Gracias, gracias Dave. And see you next time.
Hasta la próxima.
Hasta
Gracias.
luego. Gracias.